In this video, we're going to present an illustrative example to show the principle of virtual work applied to beams. In this example, a fixed ends Euler-Bernoulli beam is subjected to a distributed load Q as shown, equal to -5x1, so it's the triangular load acting downwards, and assuming that Young's modulus, the length and the moment of inertia of the beam are E, L, and I, we need to verify the principle of virtual work when a virtual parabolic displacement y is equal to ax1 squared, a is greater than 0, is applied to the beam. The first step is to actually find the solution to the equilibrium equation of the beam. The equilibrium equation states EI, the fourth derivative of y, with respect to dx1 power 4 is equal to the distributed load. The distributed load is equal to -5x1, and so we have EIY. By doing integration 4 times, we reach EIY is equal to -x1 power 5 divided by 24, c1x cubed divided by 6, c2x1 squared divided by 2, and c3x1 plus c4. In order to find the constants of integration c1, c2, c3, and c4, we need 4 boundary conditions, and the boundary conditions for a fixed end beam are straightforward. The displacement is 0 and the rotation is 0 at both ends. When x1 is 0, y is 0. When x1 is 0, theta or y prime is 0. When x1 is L, y is 0. And when x1 is L, theta, which is y prime, is equal to 0. Incorporating those 4 boundary conditions, we get y is equal to this equation, -2L cubed x1 squared plus 3L squared x1 cubed minus x1 power 5 divided by 24 EI. The corresponding moment and shear are given in the shown equation. So in order to apply the principle of virtual work, we need to find all the external forces acting on the beam. So we already know that there's a distributed load of triangular form of value -5x1 acting downwards. We also have a shear V1 acting on this end, a moment M1 acting on this end, and I'm going to draw the positive convention, V2 acting on this end, and M2 acting on this end. This is the positive convention for the equations. To find V1, V2, M1, and M2, we substitute first the value of x1 equals 0 to find V1 and M1. So substituting x1 is equal to 0 in the equation for M gives me M1 is equal to -L cubed over 6. Substituting the value of x1 equal to 0 in the equation for the shear gives me V1 equal to 3L squared over 4. Substituting the value of x1 equal L in the equation for the moment gives me M2 equal to -L cubed over 4. And substituting x1 equal L in the equation of the shear gives me a shear of -7L squared over 4. The virtual displacement applied to the beam is given in the problem as y star is equal to ax1 squared. In order to evaluate the external virtual work, we need to find the corresponding virtual displacement at the end beams. So the virtual displacement y star 1 is the virtual displacement at x1 is equal to 0, so substituting x1 is 0 gives me 0. The virtual displacement y star 2 is the virtual displacement of the second end. Substituting x1 is L gives me AL squared. The end rotation, virtual end rotation, theta star 1 is dy star by dx1 when x1 is 0, again gives me 0. Theta 2 star is the second derivative of y star. The second derivative is 2ax1. Substituting when x1 is L gives me 2AL. The internal virtual work equation states the internal virtual work is equal to EI, the second derivative of the displacement, d2y by dx1 squared, multiplied by the second derivative of the virtual displacement, d2y star by dx1 squared. The second derivative, d2y star by dx1 squared, if we differentiate this twice, gives me 2a. The second derivative of y can be obtained by differentiating this equation twice to get this expression, and doing the integral, if you use Mathematica or you do it by hand, you'll get that the integration is equal to 0. so the internal virtual work is equal to 0. The external virtual work is due to all the forces acting on the beam. The first is the distributed load, Q, value negative 5x1. So the external virtual work due to Q is equal to Q itself multiplied by the virtual displacement y star. So negative 5x1 multiplied by ax1 squared gives me negative 5ax1 cubed. When it's integrated from 0 to L, gives me negative 5al power 4 over 4. We also have the external forces V1, M1, V2, M2. The external virtual work due to loads applied at end 1 will be equal to V1 acting upwards multiplied by y1 star minus M1 multiplied by theta 1 star. And the reason is negative because we always assume that theta star is counterclockwise, but M1 in this case is clockwise. The external virtual work due to forces acting on end 2 is V2, which is assumed downwards due to the sign convention, multiplied by y2 star, and therefore we have a negative sign, plus M2 counterclockwise, multiplied by theta 2 star counterclockwise, therefore it's a positive sign, and the resulting, those two, will give me 5al power 4 divided by 4. The external virtual work is equal to the total external virtual work due to Q, due to those forces on edge 1, forces on edge 2, and so their sum is equal to negative 5al power 4 divided by 4 plus 0 plus 5al power 4 divided by 4. So they're equal to 0, and as expected, the external virtual work is equal to the internal virtual work.